To all of you? Is it visible to all of you or not? Is it visible to all of you?
Yes, sir. Yes,
Oh,
sir, Bitrus.
okay. So first thing is that just take one or two example, right? One or two example, and all the examples are solved example. And suppose a single phase 60 hertz generator, it is single phase, right? Supplies an inductive load of 4500 kilowatt, 4500 at a power factor of zero point 0.8 lagging by means of a 20-kilometer long overhead transmission line. The line resistance and inductance are given in ohm and millihenry per kilometer, right? And the voltage at the receiving end is required to be kept constant at 10.2 kV, right? So find the sending end voltage and voltage regulation of the line, the value of the capacitor to be placed in parallel with the load such that regulation is reduced to 60% of that obtained in part A and C. Compare the transmission efficiency part A and B. Actually, this kind of problem, only it is a power system problem. When you want to maintain the voltage magnitude or something or raise the power factor, generally for a circuit theory problem, you have seen that you are connecting capacitor across the load that is parallel to the load, right? So philosophy will remain same. Only thing that analysis will be slightly different, but philosophy will remain same. So the line currents, line constant R is, as line is 20 kilometer long, so multiply it, it is 0.39 ohm. And X is also, it is given, it is millihenry, that inductance, so L omega, right, into 20, because 20 kilometer is the length, so 4.52 ohm, right. This is a short line because line is only 20 kilometer long, that means this is a short line. Therefore, your sending end current and receiving end current, they will be same. As it is a single phase line, so magnitude of the current will be, this is the power, this is the power, and power factor is 0.8, so vi cos phi, right? So this is 4000 your, and this voltage is in kV, so that's why this is also in kilowatt, this is also in kV. That's why we didn't change any, multiply by here also 1000, here also 1000, no need. So magnitude of the current will be 551.47 ampere, right? And it is short line, so no question of considering the charging admittances. So IR is equal to IS, receiving and current is equal to sending and current, and it is a lagging, right? It is given that your power factor is lagging, that is angle should be minus 36 point, angle of this current should be minus 36.86 degree. So from equation 6, that is 6.6, we know the approximation Vs is equal to Vr plus I into R cos delta R plus X sin delta R. Receiving and voltage magnitude is 10.2 kV, that is this much of volt, and it is given cos delta R is equal to 0.8, therefore sin delta R is 0.6, therefore Vs you will get 11.867 kV. Now voltage regulation is sending end voltage minus receiving end voltage divided by receiving end voltage. This formula you know, into 100. So 16.34%, right? Now we want we want that voltage regulation must be reduced to 60% of that, right? That means second case, that voltage regulation required actually 60% of 16.34, that is the voltage is this much, so 0.6 into this much, so we want this much of regulation. So under this condition, so regulation will be, sending end voltage will be Vs minus Vr upon Vr is equal to this much, right? 0.09804. Therefore, sending end voltage should be 11.2 kV. That is magnitude, right? Now, if you look into the figure, that you have to connect a capacitor across the load. This is your load. You have to connect a capacitor across that, right? And you have to find out what is the value of C. This is R, this is JX, and this is the load. Therefore, if you use your again once again, if you use that your equation 6.6, so sending end voltage is equal to the magnitude of the current. This is IR. IR is equal to, actually according to this diagram, I plus IC. I is the current going to the load, right? So R cos, second case, that the delta will change because you have put the capacitor here, you have put the capacitor here. So R cos delta R dash plus X sin delta R dash, right? Since the capacitor does not draw any real power, hence the real current, right? Therefore, we can write that magnitude of IR is equal to 4500 by 10.2 cos delta R dash, right? It is kilowatt, it is kilovolt. So from this, from equation 1 and 2, from this equation and this, you can simply simplify upon substitution of all this, R, X, everything, and you will get that tan delta R dash is equal to this much. Therefore, delta R dash is equal to 22.5 degree. Therefore, cos delta R dash is 0.9238. So your power factor will improve. And in this case, and delta cos delta R is this much, you substitute here, you will get magnitude of IR is equal to 477.56 ampere. Now, from if you apply KCL here at this point, therefore IC is equal to IR minus I, right? So IR is equal to 477.56 and angle is 22.5 degree lagging. So this is your IR, right? Therefore, I is equal to, you know, this much. This is the current before you are putting that capacitor. So this is the current, your 551. This is the current and angle is minus 36.86 degree because power factor was 0.8 lagging, right? Therefore, you can easily calculate then what is IC, right? It is the your current drawn by the capacitor, right? And we know XC is equal to your 1 upon omega C in terms of magnitude, right? And is equal to magnitude VR upon IC. Therefore, you will get this is the value of XC, from which we will get C is equal to 38.5 microfarad, right? And transmission efficiency is output by output plus losses. Output is 4500 kilowatt. Whenever it gives anything without any specification, you will assume this is the output, right? 4500 kilowatt output. So this is the load, this is the output, right? So output by input, and input is the load plus loss, right? So this is I square R, that is your, in the case of, in the first case, right? Whatever it is I square R, it I is this much square into R, and in the second case I is this much. So first case efficiency was 97.43 and second case 98.06, right? And power factor also improved from 0.8 to 0.9238. Now, before moving that, let me tell you one or two things. Anything in electrical engineering, because three-phase line, so it represent by single phase because it is balanced system for high transmission line. So anything we represent, suppose this side is sending end, this side is sending end, is voltage maybe, that is we have seen for short line, medium line, long line, and this side is the receiving end, right? This is your receiving end, say angle delta R. Load is here, load is here, P plus JQ, this is the load, and this is the current I, right? It is phasor quantity, and impedance is R plus JX, right? This is the your this thing. Now, when this is represented by single line diagram, anything we do in power system, we represent, assume that they are balanced system. So each phase you consider, and in power unit system, no question of units, right? And anything you assume, right, other two phases will be shifted by 120 degree. And another thing is that whenever it is a single phase basis, if you compute the loss, doesn't matter, multiply by 3, you will get the total loss for balanced system. For unbalanced system, if you have to consider all the three phases, and in this case, for I square R for three phases, if you add, and that is not the exact losses because of the mutual coupling between the phases as well as between the phase and neutral, that is beyond the scope, right? But at the end, a little bit I'll tell you. So for P plus JQ load, when Q actually greater than 0, it is a lagging power factor load, right? When Q is equal to 0, it is unity power factor load, that is resistive load. When Q less than 0, it is leading power factor load, right? This is the for your convention. If Q greater than 0, it is a positive lagging power factor load. If Q is 0, unity power factor load. If Q negative, that means it is a leading power factor load. So this is the thing. And another thing is, suppose this sending end power, suppose the real power is this thing and this reactive power is QS, and receiving end power, real power is PR, and say this reactive power is QR. Therefore, sending end power should be receiving end power plus the real power loss of this line, that is your I square R, right? Similarly, QS will be is equal to receiving end reactive power plus Q loss. Q loss means that is I square X, right? This P loss means I square R, and QR means your what you call, that is your QS means QR plus Q loss means I square X, right? So this that means power you measure at any point of this point, right? Any point you measure, and whatever power you measure here, right? For example, suppose you are measuring power is 15 megawatts. So direction of the power flow is from sending end to receiving end, and here if you get 14.8 megawatt, then loss will be your zero point 0.2 megawatt, right? Whatever you measure here, whatever you measure here, this for real power. Whatever you measure here, it will be different, right? Because loss is there along the line. So that's why this output is that input to plus losses, right? So output by output plus losses is nothing. This is actually your I'm just making it here. It is when you put efficiency, it is basically receiving end power by sending end power. Receiving end power is that 4500 kilowatt, and sending end power is the that QPR plus P loss. That is your PR divided by receiving end power plus P loss, right? So that is the thing. So so this is your what you call, this is single phase line. Now this one again short line. You can this is your just say it's a 220 kV three phase transmission line, 60 kilometer long. Before that, let me tell us. Okay, just hold on. So 60 kilometer long. Also 60 kilometer is a short line. The resistance is given ohm per kilometer, and the inductance is given. Use the short line model. Find out the voltage and power factor at the sending end and your at sending end and the voltage regulation and efficiency when the line is supplying a three phase load of load is three phase. You have to keep in mind when it is load is three phase, and whenever it is three phase transmission line is given, it is always better that you convert it to first single phase, right? So three phase load means it is 300 MVA, 0.8 power factor lagging at 220 kV. Another is same thing but 0.8 leading power factor, right? So R is given. So the per ohm per kilometer, so multiply by 60. So this is 9 ohm. Similarly, F is 50 hertz, right? If it is in the numerical, suppose in example, if it is not mentioned what is the frequency, I will ask you, you assume F is equal to 50 hertz or 60 hertz. If you assume also, I will not deduct anything. But if it is not mentioned, you know the standard frequency in India, it is 50 hertz. Europe, it is 50 hertz. US, Canada, it is 60 hertz. In Japan, both are there. 50 and 60, both are there, right? So now this is X, you can easily calculate. Now it is a three phase, 220 kV, basically three phase voltage. So convert it to, you take it as a reference. So 220 angle 0 by root 3. You make it receiving end voltage is this much, right? Every time you convert it to per phase. Now three phase apparent power is 300 MVA, right? At 0.8 power factor lagging. That means it will be 300 angle 36.87 degree. So that is 240 your what you call megawatt and 180 megavar. In bracket it is put megawatt. This is megawatt, this is megavar. I told you that when Q is positive, that load is lagging. That's why don't take it per power. For current you can take, current is lagging from the voltage. But in the case of when it is given, it is 0.8 lagging power factor, at that time do not put minus sign, because I just told you that's why if Q greater than 0, it is lagging power factor load. If Q is 0, unity power factor load. If Q less than 0, it is leading power factor load, right? Had it been leading, then this sign should have been minus, right? That's why both the cases are there. So the current you can easily find out. Now question is that we are making A star by 3V star, right? Only thing is that before moving circuit theory, just hold on. I have not taught you first year. I cannot recall whether I taught you or not, some of you. I used to explain anything. For example, suppose somewhere it is given, say voltage is equal to, say it is given 100 angle 30 degree volt, right? And then current I is equal to, for example, say some branch it is flowing, it is going, say it is given minus 15 degree ampere, right? This is given. Now this is the suppose some branch is there, so voltage across this is 100 angle 30, right? And current flowing to this is 5 angle minus 50, minus 15 degree, and this is that your what you call, this is the voltage, this is your 100 angle 30 degree, right? So now whenever we do such thing, that if you draw the phasor diagram with respect to some reference, say this is my reference line, then if you draw the phasor diagram, then this side say it is 100 volt, it is 30 degree, so it is 30 degree, and this side is your I, that is your 5 ampere, and this angle is 15 degree. Then what is the angle between voltage and current? 45 degree, right? 45 degree. So for power equation, when we write the power equation, generally electrical engineering, we follow P minus JQ is equal to, say, V conjugate I, right? Or P plus JQ is equal to VI conjugate. But V conjugate I has a lot of advantage in computation. Later you will know, we follow this. But VI conjugate also can be used particularly for fault studies when impedance is used, right? So this is that conjugate we consider just to capture the power factor angle. Just to capture the power factor angle, right? Therefore, if you take V conjugate, that means it will be 100 angle minus 30 degree into 5 angle minus 15 degree, right? That is your 500 angle minus 45 degree, right? So that means your 500 cos 45 by root 2 minus j 500 by root 2. Therefore, P will be 500 by root 2 watt, say, and Q will be 500 by root 2. To capture the power factor angle, we use actually your conjugate, right? This is very common phenomena in our power system studies. So that's why, just one, hold on. It is not moving. So whenever it is given, for example, same thing I draw it. This side is sending end, this side is receiving. Suppose this is phasor quantity, right? This is Vs, this is Vr, phasor quantity, and current flowing through this is I, and here load is there, say P plus JQ, right? I told you the convention of this one. Now this current, I current, is going to the load, same current is going to the load. So when you write the power equation, that is will be P minus JQ is equal to Vr tilde conjugate then I, right? I tilde, it is phasor quantity. So this is that your what you call that power equation. I gave you one assignment in the previous class. Sending and receiving end load is P plus JQ. This is the clue. From this diagram only you can get that equation, that is your VR to the power 4, it is magnitude, plus in bracket something, it will be VR square, right, plus in bracket something, it will be 0. So 4 solution will be there, and only one solution will be feasible, other 3 solutions are not feasible, that you have to justify.
Sir,
Tell me.
sir, in this equation, current is known or unknown? Like you are
Which one?
saying,
Here.
no, sir. In VR to the power 4, uh, the
Here VR to the power 4, VR to the power 4, current will not come. It will be R plus JX. So this, in this, whatever will come, right? It is in brackets. It will be in terms of. I'm telling you. Just hold on. Let me move. This bracket terms here. Here I will give you the hint. In this bracket, P should be there, Q should be there, R should be there, X should be there, and VS should be there in this bracket. And here, in this term, P should be there, Q should be there, R should be there, X should be there. VS will not be here. But VS should be here. Sending and voltage is here. It is magnitude. But VS magnitude also will be in this bracket, right? So only thing is that you have to make it. Just now, I am taking first year tutorial, but your case, you did 3 hours tutorial, alternate day in lab and this thing. But at present you have now syllabus, our curriculum is changing, so tutorial class is only for 2 hours, that too also alternate week, only for 2 hours. So first one similar numericals are there, I think, in the tutorial sheet. So at least one boy asked, sir, why these 3 solutions are not feasible, only one solution is feasible? So I explained to him, actually what happened is, whatever data will be given, you have to look what is our power system need data, right? Our standard voltage level for power system is, right, higher level is 765 kV is there, 1200 is also there some country, then 400 kV is there, DC is there, but generally 220 kV, then 132 kV, then 66 kV, then 33 kV, then distribution side it is coming 11 kV, right? All are multiplication of 11, but I cannot give you any reason what is the reason for that, but it is British standard. So it is coming since then, right? So question is that whenever you get the solution, you have to see here no data is given, but you have to justify that only one solution is feasible from your little bit of so much mathematics you have studied, so much mathematics you have studied. From your intuition, you have to justify looking at the Rx, P, Q, what should be. You have to justify only one solution is feasible, other three solutions are not feasible. But no data are given, only in terms of P, Q, Rx. You can do it. You have studied so many mathematics, right? But whenever numericals are given, data are given, you have to see out of these four solution, only one solution, whatever data it is given, it is 11 kV. If it is low voltage side, maybe it is given 400 volt, right? And that value which is very close to that, only that solution feasible. If it comes 12 volt or it's come minus value, those are not feasible. So that boy asked me, sir, you please explain. So I mailed him actually detail. After that, he didn't reply. I mean, he has understood. He has sent me 2 3 times, right? So that's why whenever, at least from my side, I'm teaching first year. That right, whenever I am teaching first year, all these things I explained at the beginning of the single phase AC circuit. That how things are. So why this conjugate, right? So there will be few more things. So here in your bracket, from this diagram only you will get it. In this bracket, I'll not tell you what are the terms, right? But in this bracket, it will be PQRX, and sending and voltage also will be there here, right? And this is because we are assuming all the parameters are known except VR, and you have to, and in this parameter it will be PQRX, right? And another thing is another approximation can be made also, but that I'll tell you later, right? But in any way, so little bit you try, right? This is what, this is I am telling everything, right? This is one equation will come, this is another equation, you will get it, another equation. If I give you hint, if you can do it, that this is one equation, this is one equation, right? That means I tilde, this is phasor quantity, actually it is equal to your P minus JQ divided by VR tilde conjugate, right? And another equation from this, I tilde is equal to, this is sending end voltage, this is phasor quantity, minus this is receiving end voltage, divided by R plus JX. So this is one equation, and this is another equation, right? So two equations. Right. So if it is tilde means that is your VR tilde conjugate means VR is the magnitude, because every time I do not put bar. Whenever I put VR tilde means it is phasor quantity, and if it is not, but numerical times, just you would understand from your intuition. This is VR. If it is angle is delta R, so it will be minus delta, right? Similarly, VS tilde, not star here, is equal to VS, it is magnitude, angle delta S. So this I is equal to given this one, right? And therefore, this Vs minus Vr, your this is Vs angle delta S minus this is your Vr angle delta R divided by R plus Jx is equal to, you make P minus Jq divided by Vr angle minus delta R. So this equation you got, this equation in terms of P, Q, VR, Vs, everything. Now you have to go for cross multiplication, and you have to eliminate your, if you cross multiply you will find it is if you cross multiply it will find it is delta S minus delta R, and this will be simply VR square, because delta R and this is minus delta R, right? So you have to eliminate cos of delta S minus delta R and sine of delta S minus delta R. So what you will do, cross multiply, then separate real and imaginary part. After that, you take the square of both sides such that this cos square delta S minus delta R plus sine square delta S minus delta R, it should come to one side, so it should be 1, such that cos delta will be eliminated. From that, you will, this is a hint. I'm telling I told everything. Now you do it, right? Till I give you this thing, right? So everything you got, so then you will get equation of VR to the power 4. Try to do it. After that, you prove that one solution is feasible and 3 solutions are not feasible. So from this equation, you will only get this one. You have to eliminate delta. So bring dot term this thing, then square and add. Then cos square and sine square will be 1. And after that, you simplify, right? Hope you have understood to try of your own, right? So That's why this conjugate, when you took, look, it is a three-phase power, right? If you divide this S by 3, then it will be 100. That's why this 3 VR conjugate IR is equal to S star you have taken, because here same philosophy I told you, same philosophy, right? So 3 means it is three phase. That's why 3 into VR we are taking here is per phase. That is per phase. That's why the 3 VR conjugate IR is equal to S star, because per phase is voltage is this, so multiplied by 3. That's why IR is equal to S conjugate upon 3 VR conjugate, right? So this way it has been taken. So IR you will get this much. So from equation 6.6, again you go back to that. This is the regulation formula, voltage receiving and sending end formula, right? So you substitute VR we have taken as a reference. So it is 127 angle 0 degree. That's why it is 127, right? And I is this much, and R and X you know, and every all cos sign you know, you substitute, you will get Vs is equal to this much, right? So sending end voltage is this much, is given, that is per phase. If you line to line, where you will make multiplied by root 3, so you will get this much. So voltage regulation will be again that sending end voltage minus receiving end voltage upon receiving end voltage. Now per phase real power loss will be I square R, this much, right? Per phase receiving end power 300, it is 300 MVA, divide by 3, it will be 100 MVA into 0.8, 80 megawatt, right? So per phase sending end power, that receiving end power plus the loss. So this much. So output, I told you in the beginning some formula. Output efficiency will be receiving end power upon sending end power. So this much, right? And second case, philosophy same way you do it, but in this case this will be minus sign, because it is a leading power factor, right? And proceed same way, right? Result will be different because of leading power factor, right? And accordingly you will get efficiency, you will get 93.57, because whether it is lagging or leading, whatever it is, if you look into the current magnitude remains same, right? Therefore efficiency is not changing, but other things are changing. Regulation is now changed, right? Because voltage, your what you call sending and voltage will be different, right? So that is the thing. So this is lagging and leading power factor. Now this one I am not doing it. This one skipping. You just see this. Another example I will take, and after that we'll go to the this thing. Just hold on. Not this one. Just let me see which one. This nominal pi method. This that everything you see. Only one thing I will go. Just a minute. Where short line, medium line, long line, everything is done. Just hold on. Here. So it is a 250 kilometer long transmission line. It has impedance is given this much, R is this much, X is this much, and your generally this is your taken like this, but for particularly for a high tension transmission line, actually R will be less, X will be more, right? Because that cross section of the diameter, effective cross section of the diameter of the high tension conductor is quite high, right? And you know R is equal to rho L upon A from the resistance formula. So, but although in this part it is 33 plus J 104 it is taken, right? Generally R is much smaller actually. For high tension transmission line, if this R by X ratio, this R by X ratio is very small. It will be, it will be your, what you call, it will be always your less than 1, right? Here also less than 1, but particularly for high tension line, it may become 1 upon 10. 1 is to 10 ratio, right? So, and another thing, let me tell you, details analysis for a high tension transmission line, whatever you do, this reactance, even for 11 kV to 220 kV, whatever may be the configuration, generally, exact if I recall correctly, then it varies actually 0.27 ohm to 0.35 ohm per kilometer, right? So reactance, not much variation even from low tension to high tension, but 0.27 ohm to 0.35 ohm per kilometer. But resistance for low tension voltage side is very high compared to the, at that time R by X ratio, it may become your, it may be, it is always greater than, or it may become 2 or 3, R is higher, because power loss will be more at the low tension voltage. Because if you look into the cross section of the conductor at the low voltage side, it will be your from compared to high tension side is much less, right? So this example is taken, that one you assume this one as a short line, then you assume pi, and this is an exact transmission line, right? So Z is given and Y is also given, right? It is 10 to the power minus 3 mho, right? And receiving end load is given 50 megawatt at 208 kilovolt and zero point 0.8 lagging power factor. This is given, right? So you know root 3 vi is equal to your cos phi is equal to 50 megawatt. Here it is your 50 megawatt. Here it is 208 kV, right? That's why this is megawatt and this is kV. Megawatt means 10 to the power 6, kV means 10 to the power 3. So that's why directly it is written and it is kilo ampere, it is given, right? You can make it ampere also, no problem. So it is megawatt means 10 to the power 6 and kilo kV means 10 to the power 3. So one 10 to the power 3 will be there in the numerator. So that's why it is it is basically kilo ampere. That is 173 angle this much of ampere. You convert it to ampere, no problem if you want. And whenever anything is given three phase, your first job will be to take that voltage per phase. It is a three phase. So that's why every time if you say three phase, you make it three phase per phase, divide by root 3 angle 0 degree. This much you assume. For short line, we know Vs is equal to Vr plus Iz. Right. That is for the short line ABCD parameter. Right. That if you see the very first or second equation. Right. So from that you will get Vs is equal to this much. Then line to line will be root 3 into this much. Therefore, for short line, sending end and receiving end current both are same, right? And therefore, power factor will be, look, here that angle is 4.62 degree, right? And your this current is lagging. So that means what is the angle? Just that's why I told you here current is lagging and voltage is this much, right? That is that's why your this is the reference line and current is lagging. It is minor. It is uh, current is lagging. It is 36.87 degree and it is your 4 degree, right? So the angle between the voltage and current will be 36.87 plus 4, right? That's why this angle is your this is added, right? So you have to be very careful. Though it is minus, it is plus, don't add it because one is leading, another is lagging. You have to take conjugate, otherwise you will not get the power factor angle. Basically it will be the angle difference between the voltage and current. So that's why sending end power factor will be this much, right? And sending end power this thing will be root 3 vi cos phi, that is 52.88 megawatt, right? So this is your short line assumption. For 250 kV line, we are assuming short line, right? The next second one is nominal pi method. Nominal pi method, we know, go back to the formula that A is equal to D is 1 plus Yz upon 2. So you put all the values and then you will get A is equal to D and B is equal to Z. So this is your this much and C is equal to Y into 1 plus Yz by 4. Go back to that formula of C. So you come and is equal to J into 10 to the power minus 3. Right. So all these things, if you compute, you will get it. Now Vs is equal to sending end voltage will be is equal to AVR plus BIR. Right. Therefore, you put this A, B, C, D, then all these parameter, all you put VR, A, B, IR, everything, you will get sending end voltage is equal to this much. Therefore, line to line multiply by root 3. Then IS is equal to CVR plus DIR. So put all C, D, VR, IR, you will get this is your IS, right? Therefore, similar way, sending end power factor will be 10.23 minus, because if you look into this, IS angle is 10.23 degree, right? This is your IS and VS angle is 5.72 degree. So both are leading. I mean, both are on the above reference line, right? So not with respect to reference line. Now, if you do so, that you will find that current actually lagging from this voltage because it is 10.23 degree. It is 5. So what is the angle between the voltage and current? It will be 10.23 minus 5.72. So 10.2. That means it is like this. That means this is your reference line, right? And I think this was current. It was 10.23 degree something, and this is voltage. So this is voltage. So you have to take the angle between the voltage and current. So 10.23 minus 5 point something, right? So that will be your power factor angle. So that's why it is taken as your this thing. So 0.997 it is leading, and in that case your power will be root 3 this much, right? So because your what you call, if you see that voltage is 5.72 and current is 10.23, that means voltage lags from the current, right? This is your 52.4 when it is in the nominal pi method. Now, if you do exact transmission line equation, this all this gamma L, everything you compute, whatever formula is given, you compute, right? Here computation will be slightly more, right? With cos hyperbolic, sine hyperbolic, all these things will come, right? So, but you compute. All these parameters are given, all formulas are given, you compute, right? All these things are given. If you do so, then you will get this is the your IS, IR, power factor, everything. Now, if you compare for a short line, the line to line voltage is 235.33, quite high for short line approximation is not correct. For the nominal pi 224.85 and exact also 224.83. Sending in current is for this much for short line, but nominal pi these two are very close. Now power factor for short line is very bad, 0.75. So this and this is 0.997997. Now sending in power 52.88. Here it is 52.4, 52.4. Therefore, for yeah, your rather than assuming as a long line, right? You can represent nominal pi, right? Because nominal pi, if you see an exact one, more or less they are very close. I mean, almost same. That's why we generally in power system, even if a long line, 400 kilometer, 500 kilo long line, we represent them by nominal pi method, right? That is the philosophy. Right. So this one example is, but that's why short line is not good enough. So pi method we use. Right. Now voltage waves. I will not teach reflected wave or incident wave anything for this time. I'm last time also I think I didn't teach, right. But if you see that equation, just some imagination. Just if you see equation 26 and 27, right? The here is equal to this because it's to the power your gamma x, gamma is equal to alpha plus j beta. So if you break it, it will be C1 e to the power alpha x into e to the power j beta x plus C2 e to the power minus alpha x into e to the power minus j beta x, right? Now this is now if you convert, if you now transform this equation, right, to the time domain, the instantaneous voltage function of time can be given as now v function of time is root 2 means if we assume that is RMS value, root 2 will be the peak value. That's why multiplied by 2. The real of this one plus root 2 real of this one. Right. Only thing is that we are bringing into time domain. That's why one j omega t is given. Here it is beta x is given. We want to make it time domain. That's why j omega t plus beta x. Here also j omega t minus beta x. Right. This is from that's why we are writing it in v tx. Right. Root 2 real of this one omega t because we are making it time domain. Therefore, for two terms are there. Therefore, v2x can be written as v1 tx plus v2 tx. Right. So if you take the real part of this, v1 will be this much and v2 will be this much. Two waves are there. Two voltage equations are there. Tx is equal to v1 and v2. Now, from equations, as we move along the line, right? Suppose transmission line, along the transmission line you are moving. This phenomenon actually happens, particularly when light stroke. That your attack, what you call on the transmission line, right? That is your at that time both ends they are traveling wave, and that's very dangerous. It can unless you have proper protection, it will damage several equipment at the substation because it will travel to the substation on this side or that side, and it will be reflected back, and that will be a very dangerous for this thing for substation equipment and another. So that's why if you look at the tower, on the top of the tower you hide that one your neutral wire on, right? That is light stroke, anything happens, and it will absorb and by bypass, right? Beyond that will not cover in this city, that is maybe for high voltage side and everything, right? But this thing is there. If you move along the line, this behave like a traveling, right? Now, consider the reflected. This is actually reflected. It is just as that. But transmission line, reflected, there. I in this book that chapter is there. But I think I'm sure whether they are or not. Right. But yeah, but in NPTEL it is there. NPTEL power system analysis, I think it is there. Right. So Now consider the reflected wave. Imagine that suppose you are riding along the wave, right? Suppose this traveling wave is going on and you are riding on the wave. So if you want to see the peak temperature, right? Then you assume omega t minus that is equal to 2k pi. When there is a very equal 1, 2, 3, that P only want to observe the P. Therefore, you can make omega t minus that is equal to 2k pi. Right. As you are traveling on the wave, right. So in that case, X should be equal to this thing, and this is a type of color. This is not there. This is not there. There is not that because it is your X is equal to omega t minus k pi. Therefore, X is equal to omega by that minus k pi by beta. This is obvious, right? 6.55. It should not be there. It is a type of color, right. So it will be your omega by that t. Here I am writing omega by beta t minus 2k by beta. So t is not right. It is equal. It is your type of calculator. Right. So now if you take the speed of this x by t equal to omega by beta. Right. So therefore, the velocity of propagation is given equal to omega by beta. That velocity of propagation. Right. That is pi a from beta. Omega is equal to this. Now, if you assume a complete voltage cycle along the line corresponding to a change of 2 pi radian, the angular argument x. Therefore, the corresponding line length is divided by wavelength. Right. So a complete voltage cycle. Assume a complete voltage cycle along the line corresponds to a change of pi radian and angular argument beta. Right. Therefore, the corresponding line length, your what you call, is defined by the wavelength. Beta is expressed in radian per beta. This is beta. Again, it is a type of calculator. It will be beta lambda. It will be beta lambda is equal to 2 pi. Actually, lambda is like this, but I have it at home like this. Right. My first I like this has become heavy. Even on the blackboard, I write instead of this one. I give this one. I tell the students also. Right. Beta lambda is equal to 2 pi. Right. That is your 2 pi. Right. It is not B. So therefore, lambda is equal to 2 pi by beta. Right. Now when line losses are neglected, line losses are neglected, therefore, that is your gamma is equal to alpha plus j beta is equal to root over zy is equal to root over r plus j omega l into g plus 0. So line losses neglected, r is 0. G is 0. Right. It is r actually. Here it is type of calculator. It is r. G is equal to 0 and r is equal to 0. Right. So here that's why it is written. What to call once again I write it as a type of calculator. That T is equal to 0 and R is equal to 0. Right. That is gamma. That is gamma. It is type of calculator. Right. So here it is R is equal to 0. Therefore, lossless line you assume then theta actually is equal to omega root over LC. Right. So R is 0, G is 0. So if it is so, then from equation 29 you will get ZC is equal to root over ZY. That is root. It will become actually root over A by C. Right. So which is commonly referred to as the surge impedance. Later we will see what is surge impedance. Right. It is referred to as the surge impedance. Values for transmission line it may be 250 to 400 ohm. And in the case of cable, it will be underground cable which is 40 to 60 ohm. Right. So from 56 and 57, from equation this 56 and 57, you simplify 56 and 57, you will get velocity of propagation v will be 1 over LC. Right. Therefore, you will get E is equal to 1 over LC. Therefore, from lambda, you will get 1 by F root over LC. Easily you can find out what is lambda. Right. So now for a single phase line, now let us make the assumption. For a single phase line, inductance mu 0 by 2 pi L d upon R dash. And capacitor, 2 pi epsilon 0. Right. Your ln divided by dy. If you assume multiply ln c is equal to 0 epsilon 0 ln d upon R dash by ln d upon R. Now if you approximate ln d upon R dash is approximately ln d upon R, then LC will be actually mu 0 epsilon 0, approximately. Therefore, velocity V, right, 1 upon 1 over LC, whatever you see, from equation CF61, you will get it is approximately 1 upon 2 over mu 0 epsilon 0, and lambda will be this much. This value is approximately the velocity of the light, right? So this is an approximation, and your what you call in reality it is much less, right? In reality it is much less because we have made so many assumptions. So this is actually approximately equal to the velocity of the light, right? And lambda will be this much. So in reality it will not happen, but it is just to show you that some ideas, right? Now regarding surge impedance, that when the transmission line is loaded by being terminated with an impedance equal to its characteristic impedance. So this is actually characteristic impedance ZC, right? If the transmission line is loaded by being terminated with an impedance equal to the characteristic impedance, then magnitude receiving and current will be VR upon ZC, right? This is simple thing, VR upon ZC. But for a lossless line, ZC is purely resistive, because we are assuming R is equal to 0, G is equal to 0. So surge impedance loading of a transmission line is defined as the power delivered by a line to purely resistive load equal in value to the surge impedance of the line, that is your SIL. And it is VR square ZC, it is basically it is your resistive, and although we are writing ZC and it is single phase, if VR is the per phase voltage, multiply by 3 should be total 3 phase, right? And therefore VR is equal to your VL rated by root 3. If it is like you input in terms of line voltage, then it will be surge impedance loading will be VL square upon ZC, right? So this is one thing, and this one simple example is there. That we'll study. Now your syllabus for the I'll mail. There are 4 TAs will help me. I'll mail you. For syllabus will be, I'll mail in detail, but I'm telling you chapters for the first test. Chapters 1, 2, 3, 4 is I have not got is not there, and 5. So characteristic of transmission line is not included in your first test. It will be structure of the power system, then your inductance, then capacitance, and then power unit system. Right. So your syllabus is reduced for characteristic of transmission line. I will mail tomorrow, not today. First, 2 mails you will get from me. That is your 1 mail regarding your syllabus, everything I write, and the second mail, the details of the TAs. 4 research scholar will help me, right? And they're all my PhD students. They will help me. And total number of students 106. So each teaching assistant will handle your 26, 27 student, right? And details, exam, other thing, your video camera of course must be on this thing. And exam you will get enough time. You will join by 8 o'clock, and they will take the attendance, right? They will take the attendance fast, and after that they will everything I write on the email, but I'm telling you, and they will show you the question paper, and you please take a screenshot of the question paper. You will get probably 4 questions, and you will be given nearly 1.5 hour time, right? It will start 8 o'clock you join, let them take the attendance. From 8 to 5 they will show you the question paper, and you take a screenshot, and you answer it by your 9:30. You finish it. After that you scan it. Please write your name and roll number on every page and put it together, and you will mail to the TAs. I'll give their email address, everything. It will be mailed to you, right? And it will be mailed to you. But if my mind works, at least one problem I'll be giving you. Whatever you share and do that, it will be testing time for you, right? 3 problems may be very easy, but one problem, if I am thinking I'll give that will that will decide everything, right? Who will make what answer, nobody knows, right? But 4 problems will be given in, and there's sufficient time, so you will concentrate wholeheartedly. Power unit system, then your structure of power system, then your what you call that, your resistance, inductance, and capacitance, right? And you will try wholeheartedly, right? And it is the 3 tests will be given. So first test will be on your 9th February. I'll mail you everything, I'll mail you, right? And try to do well. So if you have any questions or not, you put me. Today I'll be closing here. Tomorrow again we'll meet, and previous 3-4 chapters. Tomorrow I'll not teach anything except very small thing. Again, after the test I'll teach. Monday I leave you. After the test, I know online it is very fast. I understand that, right? Whereas the offline mode, I used to give in the blackboard solving problem. I used to move in the classroom, right? This is my habit. For any class, I used to move in the classroom after putting something, right? I understand your problem, and maybe some of you maybe must be in the hostel, and whenever I am going out, for example, I'll go to the department after some time. So whenever I'm going to the or in the market or anything, I found very less number of students in the outside the campus. Very few, very few. I mean, very few. I do not know how many of you are in the campus, right, and how many are you are at home. But now it is much better. Now it's much better. As far as COVID is concerned, now it is much better. And anyway, so mail will be given, but number of attendance will be less, and assignment, other things. It is compared to last year, because those students, I think previously I took their some of them. I took their first year, your what you call, first. I will stop presenting. First, your what you call that first year thing. Some of them they knew me, but last time exactly 100 students were there, and attendance was always much above 60%, 80, 85 like that. And in the design course, final year I am taking, now they are in final year, right? Whether you believe or not, 96 students are there. And let me tell you, all 96 are present in every class. This is very interesting. They are final year, remember? And I will take half of their design. I may take another 1 or 2 class for them because they are writing code, right? And whether you believe or not, all the 96 students are present. That also has surprised me, right? So because I am taking this design course for last, I mean, several times I have taken, but last time because they attended this power system course, so and all the time I found out of 100. But even in the third phase of this thing, I mean before the third test, I found at least 60, 65 were present out of 100. Otherwise 85, 86 were very common out of 100. But your case, it may be, if it is morning hours, then it will be 37, 38. If it is 10 o'clock, it may be maximum 51, 52. Maybe one reason, maybe you are staying for longer duration at home or in the, now maybe some of you might have written in the campus, I'm not sure, right? Anyway, thank you very much. Tomorrow we'll discuss all these at 10 o'clock. We'll discuss all these previous chapters starting from 1 to 3 4, such that you make it, although it is online. I understand that you will write everything, right? But question is that, but my experience, at least last year experience, it is not like that, right? Although it is open book, everything, right? But still it is not like that. So tomorrow 10 o'clock we'll meet, and after this, again, after first test, again maybe in the first week of March I'll take another test. 3 tests will be taken, and whatever numericals I didn't tell you, but tomorrow I'll tell you from this chapter. When I'll ask, at least 10 days, 7 to 10 days before that, I'll ask to submit. At that time you will submit, because if you submit all on time, then you will get 30 out of 30 if you make everything right. And this 10 marks assignment, maybe one I have given, I may give another one. That will be whenever I'll tell you, please submit, right? But don't share. If you share your credit, you will get, then there will be no difference of grading. You have to be selfish. You have to be selfish in this case, right? So if you have any question, you please ask me. You have any question? No question?
No, sir.
Okay, then. Thank you. Tomorrow we'll meet. We'll discuss. I'll not teach anything. Only from first to last numerical. These are all numericals will be given, right? For your 4 chapters only. Chapter 1, 2, 3, and 5. Right. 4 I have not taught you. No need. Right. And this characteristic of transmission line has been you have been relieved for this one. Second test it will be there, such that your burden will be less for this. Right. The syllabus is very less. So wholeheartedly you should try to get 20 out of 20. Right. So thank you very much. I'm leaving again tomorrow 10 o'clock. I'll set the meeting link in the evening. Right. So thank you very much.
Thank you, sir.
Okay. Okay.